Okay, hey everyone. um, so this is part four of the video. Um, I guess for those of you who are watching who aren't in the senior design project, thank you for watching. I didn't really expect other people to really watch. I uploaded these videos on the channel as a way for my teammates to easily watch the videos. And so it was just easier that than maybe uploading in Google Drive because that way they could watch it anywhere, anytime. Plus, it's just a way to permanently save the videos. But if you've done all the last steps, you probably encountered some errors, maybe something called a floating point error. And I'm going to go over a few ways to fix that. Um, the first method I'm going to show you is not the ideal method as far as accuracy, but it should work as far as getting some solutions. Um, so what you're going to go do is go back into your mesh. And under the inflation, you're going to change this to none. So what's happening is because the mesh is refined and you do have um, a surface inflation, it's causing the equations in the solver to come across some errors. So this is the first one. Just change that to none. Um, Run it as usual, like we did before, and you should get some decent results fairly quick. The other way to do it, and I'm going to go ahead and close this out. The other way, the correct way, I should say, is to um, change some of the relaxation factors, and I'm going to show you how to do that in a second. Some of these things might look a little different, and I'll explain why in a moment. So if you go into controls, you'll notice that these values are changed. What's happening is the system is trying to solve the process, but it's going too fast. So the solutions are being solved too fast for it to be accurate in the mesh. So then when that equation goes on to the next mesh, it's not accurate. So the solution is diverging, and we want the solution to converge. So lowering these factors can help that. The caveat with that is it's going to take a lot longer um, to get a solution. And you're also going to see that if we go back into here, the maximum iterations per time step I had to up to 400 because the solutions were not converging. So you'll see, when things pop up, you'll see like iteration, 50, 100, 150. Ideally, before you get to the maximum iterations, you want to see a little exclamation point and see that it says solution is converged. That's allowing you to know that at that time step that the equations have run the maximum number of iterations to where it doesn't have to run any more iterations. If you're not seeing it say converged and it's moving on to the next time step, it means that you need to increase this number. So the problem with that is, of course, too, is it takes a lot longer. So our team's working on running these simulations through our um, high capacity, high performance HPC, high performance computing facility at our school here at FIU in South Florida. So we're working on that. But in the meantime, I guess if you guys are watching this video because you were trying to see how to run these simulations, again, I apologize for not getting back quicker. I didn't expect other people to really watch the video. So that's where we're at. Now, I can go ahead and show you how some of the solutions will look. Let me go here. I want to show my animations. So let me do a playback so you guys can see how we are, right? So as you can see, these solutions took a very long time to run. You know, unless you have access to a HPC facility, I would recommend going back and changing your meshing parameters. I will show you guys though a setup that is better as far as using the meshing if you go back and take out the inflation. So bear with me 1 second. Before I do that, I want to show you guys a few settings that I've discovered, I guess, to improve how it looks. When you're running your calculations, you're probably going to be in this this display, right? And you want it to be like this, right? So it's pretty simple. When you set up your solution animations, of course you select your contour. This it'll probably be an isometric. And if you do top, again, it's going to be kind of far away. So what you can do is you can do manage views. Okay, it's going to bring this up. And then you could just click top, right? And if you click apply, you're going to see top. It'll show like this. So you can do this to arrow over. Click camera. You want to zoom in once, zoom in again, and this should be good. So then what you're going to do is apply, close, and you're going to save it. So when you save it, you can change the name and it'll add a new view type, or you can just override the existing save name. So again, you would just hit save, and then you can click on that again, and to make sure it's saved by, let's say, click top and do apply, and then go to close and do apply. Okay, so I'm going to close this and cancel that so I don't mess up my settings. But then that should give you a nice close-up, and of course you could go even further if you want in that. I think, oh, one more thing, contours. So some papers that we've seen don't have as many colors. As you can see here, there's a wide variety of colors. You can change that. So if you go into graphics, contours, and you bring up your contour, you can do color map option. You can edit it like I did, and you'll see a bunch of spots here. So what you do is just click on each little bullet and delete it. Okay, until you get, you know, fewer colors. 3 colors I think works really good, right? And then just apply and close it out. And you can see already, I didn't change it before I ran the calculations, but you can see how now it's saved more. You're not dealing with as many colors. So when you're presenting your data, maybe in a paper, or you're not going to have as many colors, it looks more, flows better. Okay, so again, I'm going to close all this out. Like I said, this project is just not feasible on my computer. I'm running on 4 cores, and just to get to this point took hours, and we're still not hitting the max iterations in over here. So it's just not feasible for us to continue. Of course, if you have a really nice computer, like a 12 core or 16 core chip, you shouldn't have any issues. Okay, so I'm going to go to another project that I had worked on and show you guys some results. Okay, while that's loading, I just if you guys are interested, so we did this case study, numerical solution to liquid flows and microchannels. This is a paper that we're basically basing our senior design project on. It's by Risha Raj, and so it's a really interesting study. They showed how slugs form, how slug shape and size is dependent on fluid flow. They use water and oil as their inlets. They're two immiscible fluids. You can see it's a really good paper, really detailed, and so we will use this as our validation plan just to kind of simulate. And of course, our plan for our project is to design a simulation that scientists can basically use any type of fluid um, and get fairly accurate results, before actually having to do the physical experiments. So again, this is the paper if you guys are interested. It's really good, really nice paper. So this should be, so it's still starting Fluent. So 1 second. Okay, so I seem to be having some trouble. I think the workbench froze. So I'm gonna have to restart my computer, which means I'm gonna lose this video. So I'm gonna stop the video and upload this video as part 4, and then just add one more part, I guess 5, is showing the results. And I'm going to make sure before I upload this, I'm going to make sure that I indeed make the other video. Otherwise, I'm going to just redo these videos. So if you're watching this, part 5 should be available now or within the next few minutes. Okay.